thank you very much for inviting me here. I feel a little bit like a fraud in the midst of all the knowledge of CSF drainage and clinical applications with the neurosurgeons and modeling with the mathematicians and the engineers. I am from the land of the dead, neuroanatomy and neuropathology. Things do not move in my land. If they move, I get worried. And therefore, what you will see from my talk will be very standard immunohistochemistry, pathological images, and all of our experiments in animals involve intracerebral injections of tracers, and then we kill the animals, or we sacrifice the animals at very short time points, and we examine the brain. So we do not do the whole in vivo imaging of the tracer. So I've learned a lot today, and I just hope that we can compare notes. So as an anatomist, I'd like to start first. This is annoying me, I'm sorry, I need to shout. So as an anatomist, I feel like Janet Jackson as well. Anyway, so as an anatomist, I'd like to point out that the wall of an arterial, I know everybody's familiar with most of this, but I'd like to point out that there are basement membranes around each component of the artery. So there is a basement membrane of the endothelium. In tunica media, there are several layers of smooth muscle, each separated by a basement membrane. And there is, as the artery enters the parenchyma from the subarachnoid space, it takes with it a layer of pia mater, and that becomes the adventitia. That has its own basement membrane that is fused with the basement membrane of the astrocytes, becoming therefore the peel-glial basement membrane. And all of these basement membranes are connected with each other and connected with the extracellular space. Why is this important? It's important because, thank you Douglas, you mentioned that the amyloid beta is produced in the parenchyma. It's produced by neurons. We all produce it. The problem with increasing age in certain individuals is that we do not eliminate it efficiently. And that's for a number of reasons, but it's also most likely due to the fact that the brain parenchyma itself does not have traditional lymphatic vessels. So what we see, which you don't see very clearly, is amyloid beta. So this is a longitudinal section through an artery, a leptomeningeal artery, from a patient with Alzheimer's disease. And we can see that amyloid beta, probably you can see it better on this one, the red immunostained amyloid is in between the smooth muscle cells. The smooth muscle is stained in green, and co-localizing with the blue basement membranes. And actually, if you look very carefully, don't bother looking there, just look here. If you look very carefully at this artery in transverse section, so this is all human brain, I haven't got to experiments yet. This is observations on our pathological tissue. You will see that the red amyloid beta is deposited around the smooth muscle cells within the basement membranes. And this is not particular to amyloid. Here you can see cystatin C in Icelandic CAA. I was talking at lunch over the catastrophe that is happening in Iceland with this family of individuals where they have deposition of cystatin in tunica media of vessels, and those patients bleed at a young age. So this phenomenon of deposition of proteins in the tunica media of cerebral arteries is not specific to amyloid beta. However, it's most common for amyloid beta and sporadic CAA. So amyloid beta is produced by neurons, and it can then be degraded by enzymes. It can be taken up by cells. It can be absorbed into the blood via LRP. This is work from Betsas Lokovic in LA. And there is most likely drainage that I'm going to talk to you about now along the walls of the blood vessels. So unlike the experiments that you've heard so far, in order to establish the pathophysiology of the drainage of A-beta, our injections have been in the deep grey matter of the mouse brain. And I started around about the time when I met Vartan, I think, for the first time, by injecting dextran. And we piloted this so that the volume is small, because if you inject more than half a microliter in the brain of a mouse, it spills into the CSF, and you don't know if you're dealing with drainage of CSF or interstitial fluid. So by injecting a very small volume, over 2 minutes in the mouse brain, within 5 minutes you're able to see the tracer diffuse, outlining the basement membranes of the capillaries and outlining the basement membranes of the tunica media of arterioles in exactly the same pattern as you see in human CAA. So here you've got amyloid beta and human CAA in tunica media around the smooth muscle cells. Here you've got it, this time it's amyloid, it's not dextran, in tunica media in the arterioles of the mouse that was injected. The one key aspect is the fact that our time points are really very fast. So I spent the first year of my PhD 100 years ago looking at time points from half an hour onwards, and I wouldn't see anything. And poor old Roy Weller, who was my supervisor, nearly hung me off the ceiling. How can you not see anything? Well, I couldn't see anything because it had drained by half an hour. So we went at time points shorter and shorter in order to see this. We then did this with, of course, we were criticized, well, the resolution of the confocal isn't as good as electron microscope, but you can't see a fluorescent soluble molecule with the electron microscope. So what we did was we biotinylated A-beta. And for those of you that are not familiar with what the extracellular space looks like under the electron microscope, magnified 50,000 times, it's very tortuous, as described by Charles Nicholson. The spaces are tight, so there are no spaces really in the grey matter. You can see that this extracellular space between the two astrocyte end feet communicates directly with the basement membrane of a capillary. So there's the cerebrovascular basement membrane, there's the endothelium, and that's the lumen of a capillary. So there is a direct communication, but there's no space as such, because all of this is actually extracellular matrix. So collagens and laminins and proteoglycans and glycoproteins. So when we injected biotinylated A-beta, which you can detect by electron microscopy, again, within 5 minutes, it diffused through the extracellular spaces and entered the basement membranes of the capillaries and arterioles. Here you can see them nicely surrounding a pericyte in the wall of a capillary. Very recently, we've not published this yet, we've demonstrated this for tau. And again, you can see an even nicer stripy appearance of the fluorescent green tau around the red smooth muscle in the basement membrane, separating the individual smooth muscle actin staining. So the only animations or the only movement you'll see from me today are summary diagrams. So in our interpretation, amyloid beta produced in the extracellular space enters the basement membranes of capillaries and the basement membranes of arterioles. Now, it used to be called loosely perivascular drainage, and then of course the paravascular glymphatic terminology came up, and we decided to actually shake it up even a little bit more. You have to keep up with the sexy names. So we decided, well, it's intramural, it's in the wall of a vessel, it's peri-arterial, it occurs in arteries, and it's drainage. And it makes a really nice acronym, IPAD, until Apple sues us. So funnily enough, since I've been going around saying IPAD, people remember IPAD, you know, as a process. So aging is the single biggest risk factor for Alzheimer's disease. Does this process fail and why? Firstly, actually the morphology of the basement membranes of these drainage pathways changes with age. Now, in order to examine accurately the morphology of basement membranes by electron microscopy, we had to use mice rather than human tissue, because the human tissue has been fixed for long periods of time and it has a lot of artifact, and therefore, it's very difficult to perform accurate and credible electron microscopy. So we used mice that were perfused very well in two regions, and the reason we chose two regions is because CAA mostly occurs in the cortex, very rarely in the striatum or in very advanced cases. And we showed that the basement membranes of the capillaries and the striatum don't really change with age, whereas in the cortex they develop these microaneurysms, they become significantly thicker, and they change their composition, so they have more perlecan, which actually in vitro has been shown to promote the aggregation of A-beta. So it seems that as we age, the ratio of these proteins in the basement membranes change such that the environment favors the aggregation of A-beta. Now, I go back to the talk this morning, and I'm very, very interested in why these white matter abnormalities occur. And could they reflect a failure of drainage of fluid? Because actually they indicate excess fluid. Now, David Waring, who's the head of the stroke unit in University College London, has a very well characterized cohort of patients with CAA, and he's managed to follow them up until death. So he's had both the scans from these patients showing white matter abnormalities and the pathology reports. And for one of these patients, he actually managed to get biopsy tissue. So we were able to perform electron microscopy on the biopsy tissue. I have no idea why this happened. On the biopsy tissue from the CAA patient from the white matter, and compare it to normal tissue from a young patient with epilepsy. So if we look at the young artery first, I'd like to also agree with what Marcus said. There is no space in a normal, it's all occupied by basement membranes, by extracellular matrix. So yes, it's porous material, but I don't want people to think that there are these gaping spaces that are alongside vessels. In the white matter abnormalities, the morphology of the arterial wall is very abnormal. Thicker walls, all sorts of things happening in the wall itself, but then also there is this real space that you can actually see that's outlined in yellow. I wanted to know where this space is exactly, considering the compartment of the artery. So in order to do this, I needed very well perfused arteries from a mammal that is not a mouse, that actually has white matter, because the mouse just has that, corpus callosum, and that's it, and compare it to an artery in the grey matter. So we had very well perfused tissue from Biogen that funded part of my work from a dog. So this tissue, so it was sent to us already perfused, so we were able to distinguish the structure of an artery in the grey matter, where you can see here the endothelium, basement membrane of the endothelium, smooth muscle, basement membrane of smooth muscle, and in pink one layer of leptomeninges that forms the adventitia. In the white matter, there is the endothelium in green, the smooth muscle in yellow, 2 layers of leptomeninges, forming thus a potential space. Now, why there are 2 layers of leptomeninges in the white matter and only 1 in the grey matter, we don't know, but these 2 layers are completely destroyed in the white matter abnormality, so they allow the infiltration of fluid. So now I'm coming to the glymphatic. So of course, you know, in 2012 when the interest came up again, we decided to inject, well, what can we do different? Because it was all characterized and recharacterized in great detail and high profile. So I thought, well, that's all very good, but the resolution of the 2 photon is not as good as the electron microscope. You can't really see structure. So we injected nanoparticles that are electron dense into the CSF of mice, and within 5 minutes, we looked at their distribution inside the brain. And what we saw is that they are stuck in the basement membranes that are outside the iPad drainage pathways. So it's a very busy place here in the wall of the vessel. So there's the endothelium, there's the smooth muscle with its basement membranes, which is the iPad drainage pathway, which you can see is clear here. There are no nanoparticles in it. Instead, the nanoparticles are stuck in the pia mater. They're stuck in the glial basement membrane, which suggests that the route of entry along the walls of arteries is the glial basement membrane. And therefore, it could well be dependent on aquaporin 4 that is expressed on the astrocyte end feet. So far, so good, we agree with the glymphatic colleagues. Now, we then, Biogen funded this work because they wanted to know where their antisense oligonucleotides went, whereas, of course, I wanted to continue to describe the anatomical route for the glymphatic system. So we took amyloid beta this time, and against my principle of injecting it into the parenchyma, we injected it into the cisterna magna, in young mice and in old mice. And we had 2 time points, 5 minutes, immediate, and 30 minutes, which is the same time point that Michael Nedergaard and Jeff Eilif examined with 2 photon. So in a young mouse, at 5 minutes after injection of the red A beta into the CSF, we saw the red A beta outlining the glial basement membrane. And I know it's the glial basement membrane because I had an antibody specific for that basement membrane from München, where Lydia Sorokin actually has spent a whole career characterizing basement membranes. So this particular antibody is specific for the pia mater. So you can see the red A beta co-localizing with the blue antibody, pink in the glial basement membrane. But then look at what happened. At half an hour, those mice that were allowed to live for half an hour, the red amyloid beta was not in the walls of veins. It was still in the walls of arteries, but just a different compartment. It was in this spiral arrangement around the smooth muscle, essentially in the iPad drainage pathway. And here's one optical section from that confocal image. In the old mouse, nothing different from the young at 5 minutes, so amyloid beta entered along the walls of arteries into the brain. But then, at half an hour in an old mouse, we saw it in the walls of capillaries, whereas here we only saw it in arteries, and even in the walls of veins. So at that point I thought, oh well, you know, maybe the drainage does occur, you know, as a process in from the CSF along the walls of arteries and out along the walls of veins. Except, if you look really carefully, and this is where the lighting would have helped, here is the surface of the brain, okay? The amyloid beta was injected here in this compartment, yes, so we're in the subarachnoid space. And you can see it going down in concentration or intensity from the surface of the brain inwards, rather than from in here draining out. So it's sort of just diffusing along the pia mater, along the walls of veins as well, rather than this other direction. So what we've done recently is we've used an Alzheimer's mouse, and we decided to just go crazy, and we injected simultaneously amyloid beta in the hippocampus, amyloid beta of a certain color, blue, in the hippocampus, and in the cisterna magna, those poor mice. And what we saw was that, and the mouse was an Alzheimer's mouse, so it had its own endogenous amyloid beta as well. So we're talking about 3 amyloids, one that the mouse itself had, one injected into the parenchyma, one injected into the cisterna magna. We've not published this yet, and maybe after this talk we never will, but I hope not. But anyway, what we've seen is that the hippocampally injected A beta is where we always see it, in the walls of arteries, in this striated appearance in between the smooth muscle. But look at what happens here at the large leptomeningeal arteries. We see both A betas in the wall of the artery. So it is possible for that wall of the artery to have two-way traffic. Here we've even got the green, because you can see the plaques, the green endogenous A beta produced by the mouse. So it does appear that the tracer from the CSF goes in along the glial basement membrane. Sorry, I got my blob to the right rather than, in the wall of the artery. And then it drains out along the intramural peri-arterial drainage pathway. So yes, in our hands, it does appear that the wall of the artery is a common pathway for both convective influx of CSF and drainage of IPAD. And of course, what that means is that the motive force becomes even more important. I'm going to skip this and get to the fact that what drives IPAD, despite all of the efforts that poor old Alexandra, who now works in Simula, has made in conjunction with Vartan's PhD student, it's not the pulsations that drive IPAD. They're in the wrong direction, they're of the wrong amplitude, but instead it's the strength of the smooth muscle itself, which for us and for therapeutics in Alzheimer's disease is good news, because you can act therapeutically on the smooth muscle of an artery. So there are already efforts that have started in Japan with cilostazol. Cilostazol is in clinical trials already. It improves the contractility of the smooth muscle. It's given for intermittent claudication already in Japan, and it does show promise in early stages of Alzheimer's disease. So with this, thank you very much, and I thank, of course, my mentors, my sponsors. I've got to single out Roy Weller, who's my mentor, and AJ from when he was director in Biogen, all my group, very young, enthusiastic group, and the funders, of course. Thank you.
All right, well, we are running a little bit late, but I think we would have questions, and then we'll just cut the afternoon tea break a little bit short to account for the issues with the timing. So, questions for Roxana?
You just once again say, so you don't see them repeated going from the parenchyma to the venous pathway?
We don't. No. The only time I have ever seen amyloid beta in the walls of veins is when the IPAD pathway is blocked. And it's blocked by immune complexes. We modeled immunization, so we basically took a mouse and we modeled the immunization that is currently in the various trials that are failing for amyloid beta. And if immune complexes form in the walls of arterioles, which they do, then the amyloid beta, or any tracer, is diverted towards the veins. But it just stays there, it doesn't go anywhere. We find it there after 24 hours, after 7 days, it's taken up by macrophages, it just stays there.
Bryn?
Can you help us understand how you view the confounding effects of the sacrifice of the animal, and describe that, or on the findings that you have, how certain are you that these are not affected by that process?
Well, there was a paper that came out from the group of Stephen Prue last year on the effects of death. Yes, you have to account for that, but you also have to remember that all mice are killed under the same conditions, and we do see differences from the immunized mice to the wild type naive mice, which is what I've shown you. I don't see how not killing them or killing them differently will suddenly divert tracer from one part to another. I mean, there are limitations in every method. I don't do in vivo imaging. I do immunocytochemistry and experimental neuropathology. If there are artifacts, then the whole of the neuropathology discipline is questionable, right? There will always be artifacts from fixation, from death,
So a couple of mechanisms that might come into play include vessel collapse and osmotic effects, like spreading depolarization is going on. We've looking not globally, but at the spaces we can see, we do see crazy flows when the animals die, like the one we just showed.
The only question my only response to all of this is, why does CAA not occur along the walls of veins? If amyloid beta drains along the walls of veins, you would expect it to deposit in the walls of veins. And I have challenged the neuropathologists at the British Neuropathological Society, and you'd have to, out of thousands of cases that they've examined, they might have seen some A beta around a vein,
I think that's a great point, and
So
I'm not so convinced about veins.
there's that. Does Micah know that? It's on camera now.
Maybe not saying it publicly yet.
I know.
We'll see.
I've had both private and public conversations with her. But anyway, God, I've killed my career now. Anyway, so who cares? UK is leaving the EU. So anyway, the bottom line is CAA in humans does not occur in the walls of veins. And if you take transgenic animals where you engineer them living to produce mutant A beta, it still doesn't deposit in veins. It deposits in the walls of arteries. I rest my case.
Okay. Very passionate case of that. Marie?
So a bit on the Peri naming discussion. So this is a question in two parts, maybe. So where do your peri-arterial spaces end up? And do you think there are peri-arterial spaces on the surface of the brain, or is it a continuous whole?
So I actually, it's not about what I believe in. I do not see spaces. I never see spaces. I see extracellular matrix. And it's just extracellular matrix that is in the extracellular space. Well, extracellular spaces are filled by matrix, and they continue as the basement membranes of arteries. These basement membranes can be thinner or thicker, but I never see space. The only time, so actually, again, this, and I know I have the support of neuropathologists in this, the Verco and Robin spaces are actually most likely artifactual due to fixation. Because if I take a brain from my anatomy and I put it in a bucket of formalin, it shrinks at different, what's the name I'm looking for, different rates. And therefore, you can actually get a gaping space between an artery and but what is happening is that the astrocyte end foot peels off from the rest of the vessel. And then you have a space in death. But not if you have well-perfused tissue, including in human, because I really had to go begging with our neurosurgeons to try and get some tissue, to just look at, at that tissue with the electron microscope. Are there spaces or not? There are no spaces. It's basement membrane.
But if you go outside the parenchyma, so the amyloid beta should go somewhere, right? Once it has... and where does it go then?
Absolutely. so they're very credible studies by Helen Sayre from the 1980s, Jorge Guiso in New York very recently, but you have to use radio-labeled tracers for that. So you inject I've optimized my experiments so that they are fluorescent A-beta, and I can detect it for a space of up to 200 microns from the injection site. After that, it's diluted. Yes, if I inject 2 microliters of fluorescent A-beta, I'll be able to see it everywhere. But if it's half a microliter, I can't. However, if it's radioiodinated tracers, you will be able to detect them. And people have detected them in the cervical lymph nodes and in the CSF. It appears that about 15% of at least A-beta and of albumin escape in the CSF and are probably measured as biomarkers. Because whenever I go to neurology meetings, they talk about biomarkers, and I just say, do you know how these biomarkers end up in the CSF? And they go, no, that's for you to work out. But we measure them and we correlate with disease.
Okay.
There's a nice paper by Hutchings as well from 1986 that shows that in microscopy the structure of vessels on the surface of the brain. I can tell you as a surgeon, if you think about the subarachnoid space, it's not just a layer of arachnoid and then fluid and then blood vessels. It's full of trabecular.
Yeah.
But if I want to operate on a metacerebral artery analogous to what you're showing us in the mice, I actually have to pick up the layer of arachnoid that's over it and cut it off the artery to get to the artery. It's covered by a layer of arachnoid, which is quite different to what we're talking about in what has been called prevascular stasis in the brain. That's why I think they're quite different.
Yeah, absolutely. So there is a clear leptomeningeal sheet of the artery in the subarachnoid space.
Yes.
Whereas in the brain, it tapers off. The artery goes in with a layer of pia mater, but then as it branches, and I can't tell you which level of branch, but as it branches, it loses it. But it's something that we can easily work out when exactly it's lost. I wasn't interested because that's not the compartment where A-beta deposits.
All right, are there any last questions before afternoon tea? Okay,
Well,
what's the last question?
We've seen some presentations this morning of images, MRI images of presumably some of these perivascular spaces. How would you explain those?
Well, the tracers, even in our hands, enter the parenchyma as whichever name you want to give to the process. I play it safe and I call it both glymphatic and convective influx. But the tracers go in along these basement membranes. So the basement membranes are you've written the paper, so it's essentially drainage along a porous substance rather than an empty space.
All right, well, I think we will have to draw it to a close there. I'd like to thank all of the speakers for a really interesting